All right, welcome everybody to class. Class has started. Who has seen this poem before? Someone read it for us. Would you read it? Nice and loud. Kits, cats, sacks, and wives. How many were going to say knives? Someone throw out a guess. More than 100, more than 1,000. What? 74. Let's guess. 7 to the 4th. Good guess. What's another guess? 1. How do you know 1? Yes.
Oh.
The answer is 1. But it made you want to search all these possibilities, do all these multiplications, didn't it? Who here immediately thought I have to do tons of multiplications? When I first saw this, I thought that too. So when you have a space of all these things you have to explore, that is one of the problems we find ourselves up against in computer science all the time. And sometimes, as with this one, there's a really simple answer. How do you get to the simple answer quick without exploring all the possibilities? Instead of all the kits, cats, sacks, and wives, how do you know when there's only one going to say knives? We'll get into search spaces today. But first, let's talk about last week's homework. A couple people did come to office hours, but not more than only 2. I would encourage the rest of you to come on a semi-regular basis. It can be good. Now, why did we do the dumb predictor? There were 2 main reasons I wanted to do it. What do you think they were? Or do you remember me telling you what they were?
Getting used to the process.
Getting used to the process. If you did the dumb predictor the way that I asked you to do it, then everything would be in the right place in your code for doing real predictors. What's the other reason I wanted you to do it?
I guess also that skewed data can greatly determine how accurate your prediction model can be.
And then once you get out of the lulled sense of security we can have sometimes when we make something that's highly accurate. Maybe it's accurate, but your model is totally dumb. And it's accurate only because the data is so skewed, right? So later on in your career, when you make models that are working great, you got to ask yourself, did I actually just make a dumb predictor? Or would a dumb predictor be even better than what I think? There are times when I trained a model and on the test set, it actually did so poorly, it would be better if I just did the opposite of what my model said. It trained perversely. I mean, that's really bad, but that happens. Okay, a couple of other suggestions about homeworks. These are just notes that I thought of as I was going through your homeworks. In the top of the IPNYB file, just make the name of that file something that includes your name, or put your name in the description inside the file, either one. Just so that when I double click on it and I am looking at your code, I can keep referencing it and see who it's from. That helps. Someone put the accuracy as the true positive over all. All of the, positive plus false positive plus true negative plus false negative. And this was true. This is the right answer in the context of what we've been doing with dumb predictor, where every guess we make is going to be one thing. But that's not necessarily true all the time, is it? How, in terms of true positive, true negative, false positive, false negative, how would you write accuracy? If we're saying that accuracy is the number of right answers.
Oh, true positive plus true negative over all.
Yeah. So remember that for future homework where it matters. Now we use true positive. Sometimes some of you in your homework did this for a negative class. And that's fine. Sometimes it's a good practice with homework to make things as easy to understand as possible. So feel free when you have data to do conversions, to convert your data so that your zeros or ones, if you're doing something that's a little bit convoluted. I had a friend who I had trouble understanding it because he would always say things in certain ways. Like if you talk with him about something, he'd say, well, no one would say that, I wouldn't say that I don't disagree with that statement. What does that mean? When there's too many, negatives of this and that, it can be confusing to follow it sometimes. Okay. Is the confusion matrix. The way we usually do the confusion matrix is the actual labels are the rows. Label 0, label 1, in the future you have 2, 3. The predicteds are on top. Someone flipped them the other way. This is the standard. I'd like us to stick with this. One of you figured out something I like, figured out how to put a choose files button inside of your Python notebook. Raise your hand if it was you, I can't remember. Good job. Oh, really?
Yeah.
Well, it was there when I looked.
I commented it, that way, like every time you run it, it's just ask the file.
Well, I didn't run any of your notebooks. I looked at them in the state they were already in. Because I didn't want to mess something up, because maybe the file loadings will work for you, but not for me. And I wanted to see the state that everything was in. But raise your hand if you joined the new Discord channel for the class. All right, everyone, please join that. That is going to be the easiest way for you to contact TA and get help from him, and to learn things from each other, like that choose file button. If you could share the code how you did that, or instructions or something on the Discord channel, that would be great. Thank you. All right. Something that more than one of you did, I think maybe 3 of you or so, you didn't follow the model. Do you have a question? Oh, you didn't follow the structure that I asked for, but the structure I asked for was, first of all, you have a model class. You can actually call it anything. But when you define a class, if you were to subclass something else, you would put that here, but it's not necessary. Now, every class in Python needs to have an init, and so you need to have that even if you're not doing anything interesting with it. So if you're not doing anything at all, you just write pass. One of you actually found something interesting to do with it. They were taking a bunch of data and choosing, I think, some threshold, and they would pass in the threshold when they created the model. That was a good use of the init, but don't feel like you have to use it. But the predict is important, because I want you to have a predict function with a very specific structure. Obviously, since it's a class method, It has to start off with self, as all Python class methods do. But here, I wanted you to pass the data. And let's just represent the data with a big X, capital X. Then you do the stuff with the data, which for the dumb predictor, you know what that was. For the real predictors, it's going to be actually making predictions. And it needs to be flexible enough that if X has 1 data point or 1,000 data points, it acts the same. It's going to give either 1 output or 1,000 outputs. And a lot of you did this perfectly. Good job. It's important that X is actually multiple data points or a list of lists. If you're going to pass just 1 data point, it's still a list of lists, but only 1. The reason is because this is the format scikit-learn takes and other models tend to take. And you'll see later in the course why this is a more efficient way to do it. What some of you did instead is you called some function that was static. Some of you called your data the model and passed that. That's not the way I want you guys to think. Whenever you create a model, like, so let's say you had this code, and then in the main part of your function, you did something like this. Model equals. So you create a model. Then you get some data equals whatever. Let's say you read it from the file or something. Then predict on data. And either you can have this print the output or you can return it to some, results thing. Once you've created this model, what it does is it designates some area in memory where that model is going to be held. If you get some new data, you want to use the same model again. You don't want to create a new model object. That's expensive. That uses up memory and time and computation. So once you get that next data set, you run through the same model, which you can reference using the same variable. Any questions? All right. Okay. For our next homework that you're working on right now and is due this Thursday, it's a little bit unclear, I've discovered, because some of you guys have come told me it's a little bit unclear how we measure accuracy and all that. So there's 2 things we're going to do. We're going to measure it just as a regression, and we're going to measure it as a binary model. We're going to do both. First thing is you're going to take your data and divide it into test and train. So test, train, split. What should the ratio be? With that? 2 to 1. What else do people think? 20% for which?
So you give it 80%.
Okay, so 80-20, 2 to 1. What else do we think? 1 to 1. Some people think 70-30. Some people think 90-10. Some people think you should do 90-10 10 times with all the different 10s. So go at 10-fold, 10 cross-validation. The important thing to remember is that after you train, when you test, your test set needs to be a statistically representative sample of all the data you haven't even found yet. That's what you're looking for. So the actual number depends on the case. Maybe all those numbers you gave would work. Statistically representative sample of all the data you haven't even gathered. So you want it to generalize. Okay, so you're going to do the test train split. I'd suggest 80-20 maybe on the kind of data sets I saw from you guys. You're going to fit the line using the methods we've already discussed. Thinking about it as a regression, what are some of the ways we know that the line is the best fit? How do we know? You can just repeat stuff I told you last time, so that's fine. It's minimized, right? We've minimized the sum of the squared errors. So if we had a certain sum of the squared errors, and let's say we doubled the amount of data, how will that affect our new sum of squared errors? Let's say the data was distributed pretty much the same as the data we already had. Yeah. What's that? No, it wouldn't. Let's say we have done. Let's pretend this is the perfect best line. So we have some number. Yeah. You divide by the total number of what? Points?
Yeah. If we took all the same numbers, we would get the same line. But just if we add them all together, it would be, you'd be taking the, you'd have the same numbers and you have the same points. So the line that would go between them wouldn't change. It should just be repeating the same points over and over again.
Yeah, I think the word you almost said was average, right?
Yeah.
Yeah, so that's what I was trying to get out of you guys. So if we just added up the sum of the squares of all these things, you know, E for error, let's call it. So the sum of the squares is going to be a certain amount. If we added a whole bunch more points, if we double the number of points, we get all these new errors we got to add in. And this sum is now maybe approximately double what it was before. Of course, every element on its own is squared, but we've got double the number of these terms. So, but the line's not any worse. We want to have a measure of goodness that's consistent. So that's why we use the average. So in your homework, one of the ways you will report on the goodness of your model is to find this and average it over, however many points you have. Questions? The other way, so goodness by average error squared. The other way is set a threshold. Now, think about this average error squared. What's more important than doing it on the train set, do it on the test set. That's how you know how good your model is. Did this line you fit to some of the data generalize to the unseen test set? That's what I'm looking for here. Average error squared on the test set. And it'd be nice to compare, what it was on the train set. If it's the same in the train set as the test set, that means your model generalized really well. Maybe the data doesn't fit align perfectly, but your model generalized well. Now, for the last part, set a threshold. So set some number, maybe halfway through your training set, halfway in the middle of the highest and the lowest training data points, maybe like here, and say everything above it is a 1, everything below it is a 0. Then you have a new binary classifier, right? With that, you can do accuracy and F1 and all those other things we did last week. Any questions? Ooh, that's good. That's not the right kind of data set for fitting a line. You will need new data set. And to make it easy, just have one variable that's the input and one variable that's the output. In the future, we'll do linear models with maybe 10 variables as inputs, 10-dimensional or more, 1,000, who knows? So for this homework, just do one. So the example I gave before, this is the perfect kind of example. Given the size of a house, can you predict its price? They're correlated, but it's not perfect, right? That's the kind of data. Not that data, but get that kind of data. All right. Moving on from homework, unless there's any more questions. There are, come see me in office hours. Okay, these are some concepts that we'll be learning about. Maybe you'll be doing homeworks about them. And I'm not even going to define them all today. I wanted to bring them up here so you can see this slide and maybe do some of your own research, and we'll probably get to them all in class here and there. I may make you discover some of them on your own. What do you think a state space is? Let's talk about a simple situation like a chess game. What would be the state space for a chess game?
So just like the current position.
Yeah. But there's one other thing you got to know. Now, let's say you knew that in the rules. There's one part of the state you're missing.
Whose turn it is.
Yeah, whose turn it is. And that can be everything, right? Whose turn it is. Chess masters are amazingly good at state space memory for chess. There are examples of people, playing without the board. They say, king to rook 5, stuff like that. They'll say move back and forth. And they don't forget, they don't get it wrong. Why do you think that is? What's going on in their head? They can visualize it. So it's just like an image memory kind of thing?
Well, it's a combination. It's like experience with it and then be able to visualize it, realize like the possibilities. So it's a combination of like imagining it in their head, thinking of the possible outcomes, and then also like remembering the path of past decisions made, like all that together.
Yeah. One of the things he said there was super important. He said the past decisions that led to that state. In a lot of these problems in computer science or AI, we come across something called path dependence. This also comes up in complexity science. So where you can go is very dependent upon the path you've already taken. Now, an interesting fact about these chess masters is they did this test. They took a bunch of board states from famous chess games. There's thousands of them that have been recorded, right? Just choose random board states in the middle of the game, or even some non-famous games. And they have this thing where they did this with a computer, and they, when you press a certain button, you can see the board state for like 1 second, or maybe even half a second. And then you have to duplicate that on another board. How many times do you have to peek for 1 second to get the whole thing and put it on another board? Well, for the average person, it's pretty hard. And they have to peek a bunch of times. You or I would have to peek a bunch of times. Is there a chess master here in the room? No. We would all have to peek a bunch of times. The chess master will look at that board maybe once or twice and remember everything and put it onto another board. They compare them with the average person, and they're just way better. But then they created random chessboard states that didn't come from any game and likely were not reachable by any combination of moves. When they did that, the chess masters did no better than the average person. Why?
Oh, well, like the first like 20 some odd moves when you start playing, you're kind of like already decided the mechanic. So
We do have a chess master here.
no, I've just played a little bit. But so at that point you can kind of like decide what pieces you're gonna be where. Your pawn structure is pretty dependent on that too. So like recognize how they got to that position.
Is that what you were gonna say?
I was gonna say something like that, but typically you figure out lines on one side, pockets on one side. There's certain places you can have like things like that.
Supposedly, as I've had it explained to me, not that I'm a chess master, is that when they see a board, a chess master can intuit almost instinctually the probable decisions that led to that state. So they're constructing that memory in the moment on the states that may have led to it. Okay. Graph theory. What is graph theory? Nodes and edges. Yeah. It relates to real life all the time in all kinds of ways you can't even imagine. Leonard Euler, I think he was the one who came up with it, because of the bridges of Königsberg. You know about this? How many bridges? Yeah, I think it was 7. So, did I show this in class already? Okay. Well, I'll show it some other time. I don't want to get too into it, but you'll have an area of land here, area of land, maybe, one here, and maybe there's a bridge, a couple bridges, something like this. There's 5. I don't remember exactly the way the land was configured, but he was able to see that this is actually the same as, something like this. He was able to translate land and bridges into edges or vertices and edges, also known as nodes and arcs. And some people just call them dots and lines or whatever. But edge and vertex is the proper way to describe it. There's a deep field of mathematics having to do with graph theory. And it's going to apply to some state spaces that we're going to discuss today, but it's also going to apply to things like neural networks. Because a neural network is going to be, some node here that passes information to some other node. And there's also, this is a non-directed graph, but you could also have a directed graph where there's arrows and you can only go to one direction. Or maybe, you'll have a way you get back, but for this one, not. There's a lot of, many of the problems that you come across in math and computer science can be represented this way. And when you do that, sometimes it's easier to prove things about it. If you had a bunch of points in space that represented some states, each of these nodes was a different location in state space. The word solution path makes sense, right? It would be a path through state space. What do you think a search algorithm would be? Santiago, what do you think? What would a search algorithm be, given what we've been talking about? A way to make a path, through a state space.
Yeah, you like.
Yeah, you want to find one that means the smallest cost, right? Or the shortest distance. Things like that. An algorithm is really just a recipe. An algorithm for making a cake is, take flour, take sugar, take eggs, take milk, water, mix them together, do this, do that, heat the oven, put it in the oven, wait until this time step, this amount of time later. Maybe you have rules about if the oven's not perfect, you don't know exactly 375 degrees in there, you got to do some tests. So you have some if statements in there. But an algorithm is just a simple set of rules that enables you to act knowing what you know right now. In Oracle, you can look that up. Bounded above or below, having to do with heuristics. We can get into that. Admissible heuristics. These are guesses that never overestimate. And A star is my favorite of these algorithms. And we usually characterize it with Fn equals Gn plus Hn. And you will eventually do a homework about this. It would be lots of fun. Okay. Now a state space might be represented something like this. There's a starting point. And then there's options. You can go this way or that way. Maybe there's 1,000 options. Obviously, in some situations, there's an infinite number of choices you can take because maybe it's based on real numbers, but the ones we'll be discussing are a finite number of choices. Like in chess, I can put the piece here or there. I can't put it on the line in between, right? There's a discrete number of choices. If I go to the state 0, I'm limited on my next choice to go to either 2 or 3. But to get to 3, I can also get there from state 1. This is just an arbitrary set of states, but you'll understand soon how to apply this in real world situations. And now I need a volunteer. And I'm going to choose someone randomly. Come on up. So you can use the board and a black and a magic marker, any one of them, whatever, however much you want. Try to solve this problem. And anybody can help them. You can get help from the audience. The 2-gallon water. The source of water is, let's say, a pond. You have as much water as you want. You have to get exactly 2 gallons in the 4-gallon jug. And the only exact measurements you have are you can fill up the 4 and it has exactly 4 in it, or the 3-gallon has exactly 3. Give them hints. You guys don't even have to raise your hand.
You fill up the 4, and then you essentially connect the 4 into 3, so the 3's full, then you cut the connections. So
Yeah, and then I think 4 out the 3, then you have 1 in the 4.
Yeah.
And then
Then the issue comes up, is how we're supposed to get 1.
Before the 1 that's left in the 4, in the 3, but fill the 4 back up for it all.
Yeah.
If you put all 3 of it, lose the 1 you had to hurt.
No, so you have 1 sitting in 3, so you pull it up again, so you pull it into 3, and you're using 2 feet.
Gotta draw that. Draw something or just tell me, but once you think you have the solution, write it down in some format. I don't care how. Made sense and then it didn't make sense.
so I think you fill up the
Four.
four,
With all like
yeah,
all the water.
Fill that 4 with 3. And then you'll throw it into the 3. And then you'll have the 1 gallon. 4, 3 on. 3, 4, 3. And then we literally a third.
No, 4, 2, 3. 4, 4 to 3.
Yeah.
Instead of on. On 4.
Yeah.
Yeah.
I see. And then on for the. He did too.
Yeah, 4 has 1 right.
When you fill in 4 all the way in, then do the same thing. And then 2, 4 is 4.
After step 2, how many are in the 4 and how many are in the 3?
And then there's 3 and 3.
Mark it somehow, like how many are in the 4 and how many are in the 3. Maybe use some method of storing that state. How do you want to represent that state? Good. Good. You don't have to draw the 4, 3 every time because we know left is 4, right is 3. True. No. The one on the right can never hold more than 3 gallons. You only
fill this water?
No, so it's empty.
So
So
you get 0.
Every 0, 1.
That's right. What he just said is right.
0, 1. That's it. Then you'll fill up the 4 again. And then you'll fill up the third one until it's empty. And that'll leave you with 2, 4, 1.
You're doing great.
This is tough. I don't know how you guys think this.
So tell him what to do next. What's the algorithm step?
Fill up the 4 all the way.
So pond into 4, you could say. Go 4. Go 4 is good.
And then you have 4 and 1. And then you have 4 until it's like full of the third one, which is 2 gallons. Then you have 2. 4 to 3.
Yeah, okay.
Woohoo! Good job. This method of representing the state is good. This is a state space or part of a state space. And this actually is the solution path through your state space. Another way to describe it, if you just take this, 4 and 3, what you have in each, you start off with 0, 0, 2 empty jugs. And we have 2 choices. We could fill the 4 jug first, or we could fill the 3 jug first. And let's say we call that operation 1 and operation 2. Filling the 4 or filling the 3. And we also have operations that can do things like if there's space left in the 3 and you have some water in the 4, pour from the 4 into the 3, or vice versa, from the 3 into the 4. You also have options like take what's in the 3 and pour it down into the pond. Take what's in the 4 and pour it down into the pond. If you write down all of those rules, you actually end up with like 8 of them. De Palma made this beautiful slide, and it just reminds you that there is, some complexity that can look ugly. Let's say you just call these rules 1 to 8. Then we got to decide when to apply them. Now, this space we have, the space of options from those first 2 states, we can do a breadth first search, or we can do other kinds of search. We'll get to them. What would be a breadth first search? Yeah, from every option you have, go 1 step down and look at all of those options, right? That might look like this. So you try option 1 and option 2. And then you get states 4, 0, and 0, 3. And then from those, you try all the options. You can get to 4, 3. You get to 1, 3. You get to 3, 0. And interestingly, from 0, 3, you can also get to 4, 3. So it doesn't matter if you fill up the 4 jug first or the 3 jug first. Doing both of those in any order will get you to both jugs being full. Now, intuitively, you all know it's obvious. But there are many times you will write down a state space, but these things are complicated enough that it won't be obvious. So if you were programming this, you would want some elements in memory to be responsible for every time you have 4, 3. So if you get there, you don't have to have it stored in multiple places, whatever. But these numbers, in this case, are just the rule that you use to get from one node to another. Which one of these rules do you use? Now, what we're trying to get to is 2 in the 4-gallon jug. 2 gallons. Did we reach it anywhere yet? Not yet. So we keep exploring. Now, another way we can explore is depth first. And that would look something like this. We start up with 0, 0. Let's say you go to use option 1. Now we got 4, 0. Use option 2. Now we got 4, 3. Use option 3. Bam, bam, bam. We get down to here. We still don't have an answer. Well, it's not the answer we're looking for. This was, started off with, we actually have to start off with 0, 0. Then we fill 4, so we end up with 4, 0. Then we poured 4 to 3, and we got 1, 3. So this is 1, 2, 3, 4, 5, 6 steps. This might be the fastest solution. Maybe it's not. If you go deep enough, maybe you will find the solution. But with a problem like this, you could probably just go deep forever and never find an endpoint where you have to turn back, right? That first might not be the right way to go. Breadth first might not be the right way to go. Let's consider some other options. So we understand this jug problem. What if instead of jugs, we're talking about just traveling through actual space or traveling on land across America? And let's say we're trying to get from somewhere on the East Coast to somewhere on the West Coast, and you have to follow roads. You can't go straight there. You have to follow where the roads are. So you take your best guess. This is a certain algorithm called A star making its way across the country. What are the things you think this algorithm is looking at to know if it's doing a good job? Yeah, I mean, some of these roads are probably not the main highway. It looks like it's trying other little roads. And like in here, it's still trying, but these are so slow. I mean, it's possible to get across America using just side roads, but gosh, it'll take a while. Do you think it will eventually find the optimal path? Have you guys ever heard of the Cannonball Run? What is it?
Then, it's somewhere in New York, like Los Angeles, it's not.
What's the record?
I mean, I know it's been broken a bunch in COVID, and so they didn't really count those. I would say it's under 25.
It is. Well, no, I think it's like 25, 2600, somewhere around there, but what? 2539. All right. Do you know what kind of car it was? That was the one, I think, that made that record. Yes. This guy had an unmarked police car. So it's not against the law to have an unmarked police car because it's not marked as police, right? But everyone thinks it is. And it was this really nice, powerful Audi. And yeah, they did it during COVID, which is perfect because there wasn't much traffic. There weren't many cars in the road. They did something we probably will never do again. Because in the future, we're just going to get better at having those speed traps, things like that. They had people working together with them to take the speed traps for them. So they had a bunch of people stationed across the country, knowing where the speed traps were. That person would drive in front of them, 150 miles an hour, and the speed trap would, go after them, so that when they came by, they'd be fine. And they're communicating on the radio. Guys before them, before COVID, this one team, they had air support. They had airplanes in the sky that would be looking for these speed traps and tell them when to slow down. Okay. Another algorithm is Dijkstra's algorithm. This was famous for a long time. I don't personally like it, but it came earlier on. Dijkstra was, of course, one of the great computer scientists. He's the one who asked that question about, can a submarine swim? And his algorithm, basically, it's going to be let's say we were starting in 1, we've got to get to the 5. And it's going to be trying out certain movements and seeing how you're doing from there. Now, unlike the other state diagram we looked at, these numbers do not represent rules. Forget about that for now. Usually when you see something like this, this represents a cost. A cost from getting from 1 to 2. Cost from going from 1 to 2 is 7. Sometimes you don't know that cost until you do it. Let's pretend you're trying to get across America, and there's 2 different highways you can take. One of them maybe is bigger and faster, but the other one has less traffic. Which do you take? With nowadays with Google Maps and them understanding traffic patterns and how many people are on the road right now, we can do this better than ever before. But in the past, you couldn't. You didn't know the cost of choosing this path over this path until you actually take the path. Now, why can't you just take all the paths? It would take too long. It would take too long. Computationally, it's a bad choice. And in a game like Go, you guys know, who doesn't know the game Go? So the game Go is this board with a bunch of lines that are, going on grid, but you don't play on the squares, you play on the cross points. And there's black and there's white. And you try to surround your opponent. There are so many options to consider play that the best supercomputers in the world still cannot play all future states. You don't have no computing power. This is very simple, but in real world scenarios, there are too many paths to try. You literally cannot, or it's just not efficient, to try every one of these and figure out which is the right way. This is basically the same almost as the traveling salesman problem. And that problem is in a certain class of problems, which I know some of you know. Someone tell me the class of problems that the traveling salesman problem is in. How about you?
I don't know, like the name of the class, but it just deals with boiler paths.
We called it earlier when we were talking in office hours. No, NP complete. Non-polynomial time, which means it's worse than exponential, or it is exponential. Yeah. Polynomials are, x to the squared, x to the fifth, whatever. This is worse than that. And the traveling salesman problem is one of those problems that's worse than that. It's really bad. If you want to find the optimal path, you have to try them all. We don't want to do that. So what do we do instead? We come up with algorithms that can help. Now, what's nice about these graphs, this is graph theory here, note the net is, we can come up with algorithms that will find the best path, assuming we have a good heuristic. What's a heuristic? It's like a guess. So if I'm trying to get to the far right corner over there, I want to know if I'm taking the right path. Obviously, I don't have a lot of choices, but if I did, I would be taking a guess as how far I am from my goal. Now, maybe if I want to get there, I take a step here, like I'm closer to my goal. Oh, look, I'm even closer. I'm closer. I'm closer. I'm closer. My heuristic can tell me, yes, I'm closer to my goal now, but I'm not going to get there this way. This is a dead end. But sometimes you don't know it's a dead end until you start to take it. So if I were doing just depth first, you got to go all the way down this path, and then all the way down this path, and then all the way down this path, and eventually you go all the way down that path, and it gets to the goal. If I were doing breadth first, maybe I'd go a little bit here and calculate my heuristic. Go a little bit here, calculate my heuristic. Go a little bit here, calculate my heuristic. And if I have a good heuristic, it'll tell me this is the best out of those three. Then I do it again. I go here, here, and here. Okay, this is the best. Here, here, here. Okay, this is the best. Then I keep doing that. And maybe here I have a little trouble. I have to go down dead end here before I go down there. But it's faster. I didn't have to explore anything here. Dijkstra's algorithm will give you the best path eventually without having to explore them all, which makes it different in this case from the traveling salesman problem, because the traveling salesman problem, you have to explore every path to know that you have the right path. But this is different because you have a heuristic that you can trust. The heuristic is admissible, which means it never overestimates. And the only way to really get a feel for this is to do it in homework, which you guys will. Well, let's look at some more examples anyway. This is Dijkstra's algorithm, and you can just try to get an intuitive sense of what it's doing. So you try those, and now these are known. These are part of the known set. When something's part of the known set, you don't try it again. So from every point that you moved out, you want to know what's around there. But you're trying to focus on the ones that you think are best. Okay. Now, here's Dijkstra's in another situation. There are things that we don't think of as AI anymore, but they were AI in the beginning. Getting through a room was AI at some point. How do I get from the red to the green in the best path possible? If there's a wall in the way, an unknown wall. So let's say it's a Roomba we're talking about, and it's got to get to the green from the red. It doesn't know the wall exists. It has to find that out as it goes. This is how Dijkstra's algorithm does it. The reds are all the places where it's already been. The blue is where it's exploring now. The edge of its own. When it hits a wall, it marks that with a dark dot. Anywhere in this reddish yellow is what it knows about, and it stores it in memory. So it can use a lot of memory. Now, what you want to understand here is how fast did it do this? And that comes down to how many places in the space it had to explore. Look at that, it found the path. That is guaranteed to be the most optimum path. How much of the space did it have to explore to find the optimum path, percentage-wise? More than 80. Yeah, it looks like 90% to me. So, well, let's look at A star. A star is my favorite of these types of algorithms. So what you notice is that it went straight toward the dot, but it keeps bumping into that wall, right? Ooh. Found the optimal path. Now, I think there's only one optimal path, so it found the same path. What's different about this algorithm?
It tries to directly go.
It did.
The wall, and then it keeps going to the sides. It's constant, and it's trying to go directly.
How does it know what directly means?
It calculates the shortest distance. The wall wasn't there, then it goes that way to the wall. And starts putting dots on the side. Still calculates the shortest distance. Trying to get
What kind of distance metric do you think it uses? Euclidean, yeah. So it starts off at the beginning, calculating the Euclidean distance from itself to the end. So, you know, it starts off here or whatever. When it goes here, it calculates a new Euclidean distance. And for here and here and here. And for everywhere it's been, it knows the Euclidean distance to the target. Now, some of these, of course, hit dead ends, so it can't use them. So then it goes to its next best guesses. And then the next best guesses, then the next best guesses. Until it's starting to wrap around here. And it's like, oh, this is promising. So it orders its search. It's not depth first, and it's not breadth first. We might call it best first. What's your current best option? I'm going to search there. Okay. Remember that equation near the beginning? Fn, Gn, Hn. Gn is the cost you paid up to now, wherever you are. Hn is your heuristic of how much further you have to go. You don't know about walls, maybe new walls. Maybe this new path you take is going to be full of traffic. The one thing you don't want to do is overestimate. You want an admissible heuristic. Now, is there a situation where that's not true? Maybe it's okay to overestimate it. Sometimes, are there other things you want than the optimal path? Maybe you don't care about perfection. What else may you care about? Scenic drive. Oh, that's good. I didn't even think of that. You know, when the Germans built the Autobahn, which I've driven on, and it's awesome, they actually cared about it being beautiful. It's not like highways out in the western part of the U.S. where it's just straight forever. They try to make it bang and try to show off beautiful mountains and lakes.
Maybe like construction, instead of just having functionality, new priority.
Mm-hmm.
I was gonna say, the Kiwi box, if they like detect a human in front of them, they might not try to go like an inch away from it, but have some sort of clear clearance around it to try to go like a foot away from it. to match.
Respect to other entities. We might call like cognitive load. That's one thing we do discuss in university, UX or user experience. You want to have a low cognitive load. And even if it would save me 5 minutes, I'd rather just stay on the highway. Then I can just listen to a radio and drive along. But there's another reason. Maybe you don't care about the optimal path. You want a good enough path, but you want to be able to find it more quickly. So let's look at what A-star does when you relax the admissibility just a little bit. Let's say some small epsilon. You could say, yeah, we might overestimate sometimes within some epsilon. Then, well, then you get this. Look at that. It's not exactly the same path. It's not perfect, it's not optimal, it's probably one step more. It's almost optimal. How much of the space did it have to explore? Yeah, it must, maybe less than 50%. So when you can get good enough without being optimal, this is what we tend to want to use in the real world. This is probably what Google Maps is giving. There's lots of other math going on behind the scenes, and Google Maps probably uses a set of algorithms called course to find instead of A-star, but there's some hints of A-star in what they're doing. A-star with the non-admissible heuristic. Kind of nice, isn't it? You guys will be programming something akin to this at some point in one of your homeworks, somewhere in between that and this. You will be searching a space in order to play a game. All right. Any last questions? All right, thank you, everybody.